Welcome. My name is Julie Gunkelman. I am the Professional Development Coordinator for Schematic, and I'm excited to bring you the last of our 2016 webinars this year, Bootstraps, an intuitive introduction to confidence intervals with Robin Locke. This presentation is sponsored by the Joint Committee of Schematic and the American Statistical Association. One of our core values at Schematic is for professional development, and it is specifically building expertise and exhibiting leadership in enhancing and teaching and learning of mathematics, enhancing personal growth, and improving teaching methods and effectiveness as a personally initiated lifelong responsibility. So that's what we're doing here today, right? We're trying to enhance our learning. For more information, please see schematic.org. Please note that the views expressed by the presenter are not necessarily the views of Schematic. Commercial products mentioned by the presenters are not endorsed by Schematic. WebAssign is our proud sponsor of our webinar series this year. And I do want to include a short biography of Robin. Robin Locke is the Burry Professor of Statistics at St. Lawrence University. He's a fellow of the American Statistical Association, a member of the committees that developed and more recently revised the GAZE, the Guidelines for Assessment and Instruction in Statistics Education, and the inaugural winner of the ASA's Waller Distinguished Teaching Career Award. He has co-authored a textbook with his wife Patty and 3 statistician children, Carrie, Eric, and Dennis, titled Statistics, Unlocking the Power of Data, that features using simulation-based inference for introductory statistics. So I'm going to go ahead and turn it over to Robin now. There you go.
Okay, I'm trying to get it on here. Hang on a second.
Welcome.
Are we live now?
We are.
Okay, great. So thank you, Julie, for all your help in getting things set up and ready to go here. And especially thank you for people who are taking some time off in what's a very busy time of your semester and quarter for a lot of people. I know we've got our last day of classes tomorrow, so I know people are probably lots of busy on things, so it's good to, you can take a little time out to talk about bootstrapping. As Julie said, I'm at St. Lawrence University, which is in very upstate New York, a small liberal arts college, essentially in Canada, and we do have snow out the window there, so we are up in cold country. And I do have to introduce you to the rest of the family. Julie mentioned them briefly, but this is my family. My wife Patty is also here at St. Lawrence. She teaches math and statistics, and she's also part of the Hughes-Hallett Calculus Consortium. Working with that group. And then we have 3 children. Our oldest daughter, Carrie, got her PhD in statistics at Harvard and is now in the faculty in the stat department at Penn State. Middle child, Eric, got his PhD in statistics at North Carolina and is now in the biostat department at Minnesota. And the youngest child, Dennis, just last week or 2 weeks ago, defended his thesis in statistics at Iowa State, but he's taken time off now and he's off working as the head of analytics for the Miami Dolphins. So it's kind of an odd family that there's such little variability in that everybody's a statistician. But we sort of had this idea of trying to think of some different ways to teach intro-stat, inspired a lot by George Cobb's comments at USCOTS a few years ago, where he was saying people should use more simulation-based methods. So to contrast those to get started, if we think of 2 approaches to teaching inference, the traditional approach, which probably a lot of you use and have been used for a long time, is to assume some sort of distribution like a normal or a t to describe the behavior of some sample statistics. And then we use the data to estimate some parameters of that distribution. And then we calculate desired quantities we might want to have, like the endpoints of a confidence interval or the p-value for a test from that theoretical distribution. And what the simulation approach does, and this SBI stands for simulation-based inference, is basically goes through and just generates many, many samples via computer and have that show the behavior of sample statistics, and then calculate whatever quantities we want to find, like the endpoints of a confidence interval or the p-value for a test, from that simulated distribution. I'm going to talk about kind of how we use this simulation-based approach. There's a number of projects out working on this now. The one that we're working on is a textbook. There's a web address for that here. There's also another textbook by Nate Tintle and a bunch of really good folks, Statistical Investigations book. There's some folks at University of Minnesota that use the Catalyst project, and they've got some materials there you can also get that use simulation-based methods. Josh Tabor and Chris Franklin have another book Statistical reasoning in sports, which is geared towards a high school audience, but does feature all simulation methods throughout. And if you've seen the open intro statistics text, they have a version based on randomization and simulation also. So there's a number of different resources you can use to find out more about actually teaching with a simulation-based approach. And to give you a little idea where this fits in the curriculum, here 10 years ago was the curriculum I was using, and this is probably maybe similar to a lot of you are doing now in terms of how the things are organized. You may not get as much to some of the advanced methods, the ANOVA and so forth in your course, but this is a fairly standard, what I call traditional approach to teaching statistics. And so what's going to change is we'll get rid of normal distributions. We'll get rid of sampling distributions. Okay, and we actually decided to rearrange these first two because it kind of makes sense to talk about data production first. Where does data come from? And then talk about how to describe it once you know where it comes from. And notice that leaves this big gap now. And so into there will fit the Bootstrap confidence intervals and the randomization hypothesis tests. And then we will go back after we've done those and do the normal distribution. And notice the rest of the topics also get done. So one important thing about this approach is we're not abandoning traditional methods. What we're doing is trying to use the simulation-based methods early to give students a good intuition of how those things work, and then come back and later on cover some of the traditional methods. I'll talk later on in the webinar about how we might make that transition later on. So these two new areas, if you think about randomization-based hypothesis tests, I'll strongly recommend a really good webinar in the Schematic series, which you can get online, that Alan Rossman and Beth Chance were part of that Tinto group, did that really focuses on the randomization-based testing aspect of simulation-based inference. And so I recommend that webinar if you want to see more about that. And I'm going to focus in this webinar particularly on the confidence intervals. And so if you want to know about that, then stick around for the rest of this webinar to find out more about Bootstrap confidence intervals. Okay, so some of the things questions I want to address is what's bootstrapping? And maybe not something that you're necessarily familiar with. So what is it? How can we use a bootstrap distribution to find a confidence interval? And then let you think a little bit about, can bootstrapping really be made accessible to intro stat students? And even more, that can be the way to introduce students to the key idea of confidence intervals. Now, again, to use these sort of methods, you don't necessarily have to totally redesign your course. It's something you could just put in an example or two, spend a day or two on. You don't necessarily have to do the total rearrangement of your course, but it's kind of interesting to think about using these as ways we're going to introduce students to ideas of confidence intervals rather than traditional methods. Okay, and let me talk a little bit about why bootstrapping works, because it does seem a little bit magical, and especially some math folks, when they look at this, say, no, that you really can't do that. It doesn't seem legal to do these ideas. Okay, and then we will talk about making the transition to traditional methods. Okay, so again, a reminder where we are in the course. Okay, so at this stage of the semester, my students are starting bootstrapping. They've seen data production, so they've seen random sampling, they've talked about random assignment, they talk about experiments and so forth. They've seen lots of graphical displays, so they know dot plots, histograms, bar charts. We've also done some regression and some scatter plots. So they've seen lots of statistical things and lots of summary statistics. So they know what calculating means and difference in means and so forth for quantitative data, proportions for categorical data, correlations, standard deviation. So they've seen lots of summary statistics. So the question at this stage is, a natural question is, once you know how to calculate those summary statistics, how accurate are those? So when you calculate a proportion to estimate that in the population, how accurate is it likely to be? When you calculate a mean, how close is that likely to be to the mean in the population? So it's a very natural question to follow once you've done the basic summary statistics that I think we all do on our intro courses. So I'm going to look at one example through the first part here. Question is, what's the average price of a used Mustang? And this comes from some data my students collected. A student one time went to autotrader.com and shifted through a bunch of sites like this where they saw advertising for different Mustangs. They were particularly interested in buying a Mustang, and recorded things like the year of the car, the mileage, and the price. And we're going to be focusing mostly on the price here. So we'll think of this as our sort of representation of this sample of 25 Mustangs. And here's the distribution of price. This is in thousands of dollars. Here's some summary statistics for that. So for the 25 cars, the average price was about $16,000 with a standard deviation of about $11,000. Okay, and so that's our best estimate. Based on our sample, we can guess at about $16,000 is the average price of Mustangs, but we don't know how accurate is that estimate. Okay, so our goal is going to be to find an interval which is likely to contain the mean price of all Mustangs, which we better know is, of course, a confidence interval. And the key thing we need to know about to find that is we have to think about how much do we expect the mean price to vary when we take a sample of 25 cars at a time. So if we're sampling 25 cars, we're going to get a mean. As we go from sample to sample, how much do we expect the mean to vary? And we can use that as a basis for come up with a confidence interval. Okay, now if we look at basically how the traditional method does, and I'll do this pretty quickly because we're all familiar with this, I hope. The first thing we do is check conditions. And so we say we got a sample size less than 30. We've got a distribution which has clearly got some skew in it. So, hey, we're stuck. Okay, we can't do it because we don't have the conditions we need to use a t-distribution, so we're out to lunch. Okay, but of course we say, well, we'll wave our hands and say, well, we'll proceed with caution and go ahead and do the technique anyway. Okay, so then we've got to pick a formula, confidence interval for our mean. We go to our memory bank and pick out the right formula. Okay, we say I need some summary statistics, so I'll calculate, I need a mean, a sample size, and a standard deviation. We'll get those. Okay, then I need this t star value is the last thing I need here. So I've got to go and find my t-table. There's the good old paper t-table. And decide on, let's say, 95% confidence. So I want to find the 0.025 level in each tail. So I'll pick that. I've got to pick a degrees of freedom. So that we know is n minus 1. So I'll find the 24 here. I'll go across the middle. That gives me 2.064 as my t-value. Okay, and there's just a matter of plug and chug, dump everything in there, do the calculation, and then, of course, when we're all done, make sure we do a good interpretation of all that in context. Okay, so that's typically when I say the traditional method. That's what I think what a lot of us have often done as a way of calculating confidence intervals. And it is a reasonable, feasible to get students to go through this process, and they can go through and follow the steps and crank out an answer. And that's something you could do relatively well. But the answer works well. The question is that process that they're doing to get that answer really very helpful at having to understand what's going on with a confidence interval. Okay, and that's where I think the method gets a little bit shortchanged. So can we arrive at the same answer, get the same sort of confidence interval, okay, with a method which also builds some understanding? And I hope the answer here is yes, but we'll see if you agree with that as we go along and see how we do this. So the key concept is how much does sample statistics vary from sample to sample, okay? And in a specific example, we're saying if we take a sample of 25 Mustangs, okay, what's the distribution we should expect to see for the sample X bars? We took lots of samples of 25 Mustangs at a time, look at all the X bars, what sort of distribution should we see? So that, of course, we know is a sampling distribution. And so when we look at traditional approaches, typically we've got several ways of getting at that sampling distribution. One way is to know the value of the parameter of the distribution of the population. So we assume that Mustang prices are normally distributed with some mean and some standard deviation, and generate things from that, okay? Or we could take thousands of samples from the population. Okay, and that may be a little bit impractical to do if you actually sample from real population, okay? Or we rely on the theoretical approximations, okay? And I think what's pretty clear is that the first two options here are really not practical in real situations, okay? We don't know the value of the parameter. We probably don't know the distribution of the population, okay? It's not feasible to take thousands of samples from the same population, okay? So those really you can't do. And relying on theoretical approximations is something I think is difficult for the introductory students to deal with, because you got to go through a lot to get to those introductory methods. Okay. So the question now is, how can we figure out how much the sample statistics vary when we only have the information in that one sample? Okay, that's the challenge. All we have is those 25 Mustang prices. Can we from that figure out how much the samples are going to vary? Sample means. Okay? And that's where the bootstrap comes in. Okay, so bootstrapping, here's the father of bootstrapping was Brad Efron at Stanford. Invented this in the late 70s, early 80s. And for those who don't know, students often don't know what a bootstrap is. Here's a boot, there's the straps. And so the idea is that helps you pull your boot on, or even if you believe some things, if you pull hard enough on those straps, you can actually pick yourself up in the air by pulling on your bootstraps, okay? And that's almost as magical as bootstrapping seems to see, that you can use the single sample itself to tell you something about how the variability of the means from the population. So here's the basic idea, okay? What we're gonna do is take our original sample and take many samples with replacement, that's very important, with replacement from the original sample, using the same sample size to use that to see how the statistics vary. Okay, so we're sampling with replacement from our original sample and using the same sample size to see how things vary. Okay? And so what behind all this is we're assuming the population is many, many copies of the original sample. So when we talk about a representative sample, what we're usually saying is the population is many, many copies of that sample. That's the key thing we're looking at here. So to give you a little schematic for this, suppose we have a very small sample of 6 people, and we're interested in some aspect of these 6 people. And all we have is those 6 people. We know nothing else besides what's going on with those 6 people. So we're assuming the population, the best we can guess, the population is lots of copies of those 6 people. If we're not willing to assume other things about what the distribution of the characteristics might be, the population looks like lots of copies of those 6 people. So we'd like to sample from this population. And the way we do that is to sample with a replacement from this original sample. So look at these 6 things. Maybe we roll a die. We roll a 2, and we get the blonde person. Okay. We roll a die again. We get a 6. We get the redhead. Okay. We roll a die again. We get a 2. We get the blondie again. That's fine because that blonde represents lots of different blondes in the population. Okay. We get this nice round person. Okay. Maybe we get that round person again. And maybe kind of this mean-looking person here. So there's our 6 people. There's our sample size 6. That's 1 bootstrap sample. And whatever statistic we may have calculated in the original sample, we can calculate that same statistic on this sample here. So that's the basic idea of how bootstrapping works, is to sample with replacement from the original sample to generate a bootstrap sample and then calculate our statistic from that sample. So if we think of applying that to the cars, here's our 25 cars with a mean of 15.98. And so I'll randomly sample 25 cars with replacement. Okay, that's a little bit tedious to do, but you can think about doing this even in a classroom. If you have a bag with 25 little model cars in it with prices written on them, the idea would be you shake up the bag, pull out a car, write down the price, put the car back. Okay, shake it up again, pull out another car, write down the price, put it back. Do that 25 times to mimic the size of our original sample. That's 1 bootstrap sample. Okay, find the mean for those. We've got the mean for our bootstrap sample. Okay, and that's a little tedious even to do for 1 sample of size 25, but we want to do this thousands of times, okay, to really get a good idea what the distribution of the sample means looks like. Okay. So again, so schematically here, we get our original sample. From that, we draw our sample statistic. And then we get lots and lots and lots and lots of bootstrap samples. For each of those, we calculate the bootstrap statistic. Put those together to get the bootstrap distribution. And then we'll see how to get the confidence interval from that distribution in just a minute. But clearly, if we're going to do this thousands of times, we're going to need some technology. Okay, and there's several things you can use for technology. Or the one I'm going to demonstrate today is called StatKey. It's a website. Here's the website for it, lock5stat.com/StatKey. This is a freely available web app, no login required, so you can bump out of the webinar right now and go and try it if you want. Okay, it runs in almost any browser. In fact, I think modern browsers, it's hard to find any that won't work in now, but it also works in tablets, smartphones. I've had students use it in all sorts of different platforms. Seems to work in lots of different places as long as you have internet access. You can get it to go. Even if you don't have internet access, there is a Chrome app available. So if you're using Google Chrome, you can download the StatKey app and then it becomes part of your Google Chrome, and you don't even need internet access to get it to work. Okay? And you can use this as standalone. We've got enough built in there to support most of the stuff you would do in a standard intro course. But a lot of people use this as a supplement to existing technology. I use Fathom as the stat package in my course. My wife uses Minitab. Other people use Jump. Lots of other different possibilities. Any kind of a package you may be using in your course now, you can use StatKey then as an addition to that, specifically for doing these simulation-based methods. And there are some other things. Jump, for example, is a package which has lots of bootstrapping things already built in. So there are other stat packages which you can use for doing the bootstrapping. Okay, just a quick tour of StatKey. We try to keep it very simple, so everything works off of one page here. You can never get more than one level deep. Stuff you might do in that beginning part of the course, the standard descriptive statistics and graphs, that's all set up over here. The part we're focusing on, oops, I forgot this part, sampling distributions are here. We're focusing today on confidence intervals, so we're gonna be looking at a lot of these. These are different sorts of things we'll be able to do confidence intervals for. The other part of the simulation-based inference randomization tests would come here. When we make the transition to theoretical methods, the standard distributions are all also available in StatKey. And we have a few more advanced ones where you can use randomization tests for things like analysis of variance for difference in means, regression, chi-square tests, that sort of thing. Okay. And finally, one thing people miss is down in the very bottom corner here, there's a help button, and that will take you to a help page where we've got lots of instruction on things like how to get data into and out of StatKey, but also there's some videos there where we go through and have students be able to go through and see a little video on how you do a bootstrap distribution, how you do a randomization, and so forth. Okay, so I think it's time now to see if I can do the switch. So let's see if we can get things to work here to switch to StatKey. So I'm going to switch over here. And hopefully StatKey is visible now. Julie will give me a thumbs up. We're good there. Okay, so here's StatKey going live. And so to do the Mustang price data, we're going to go here to a confidence interval for the single mean. That will bring up this one. Now we do have lots of data sets built in. These are all data sets from our textbook. So there are a bunch of built-in data sets here, but there's also options for you to enter your own data. We'll do an example later on where you're entering your own data. But I'm going to go here and find the Mustang price data since that's already built in. So over in this part of the screen, we see the summary information. By the way, there's a presentation mode here in StatKey, which is better for using in classrooms. It just makes some of the text a little bit bigger. So here's the original sample of Mustang prices, the summary statistics for that. And so now we're ready to take one bootstrap sample. So I'll come over here and generate one sample. We'll start nice and slow. And so here's the first bootstrap sample. And notice, for example, this very expensive car that was $45,000 didn't get picked at all. Okay, some other cars like these in here, the $11,900 car, those got picked multiple times. Okay, and so what you're going to find is here's 25 cars chosen at random from these 25 cars with replacement, which allows the same car to repeat more than once. Our cheapest car of $3,000 actually got picked, didn't get picked at all. The $4,900 car got picked 3 times. Okay, it was only once in the original sample. So there's one bootstrap sample. There's the mean for the bootstrap sample here at 14.32. Here's the second one. Okay, so there's another bootstrap sample. This one seemed to get more of the small cars, had a little smaller mean down here at 12.84. That shows up over here. And of course, you could do this 10 at a time, 100 at a time. That's no fun. Let's do it 1,000 at a time. Okay, or do a couple thousand. Okay, I don't want to do too many because I want to make sure you still see the original dots. With my students, often if they do this 4,000 or 5,000 times, that's plenty to get a good idea of the distribution. So here's a bootstrap distribution. Okay, and this is organized pretty consistently as StatKey. We always keep the original sample over here. Here's one bootstrap sample, and over here's the summary of all the bootstrap samples. And one of the neat features is if I hover over any of the dots, watch what happens in the bootstrap sample. As I hover over any of the dots, it will remember exactly which sample that came from. So it's very good for students because they got lots of distributions to keep track of here, to keep track of the difference between the original sample, one bootstrap sample, and this big plot here where every dot here is the mean for a different bootstrap sample. Okay, so that gets us to a bootstrap distribution, and that's what we're ready to get to find some confidence intervals. I'll go back and see if I can share back here. Okay, there we go. Okay, and so hopefully I didn't share that right. Let's try again. It's not coming back for me. I should be seeing the PowerPoint here, and I'm not.
Yep, you are. We're seeing your PowerPoint.
Okay, well, that's right. It was showing the stat screen. No wonder. It was just showing exactly what I had on the other screen. So I did see that. Sorry about that. Okay, so so here's a typical bootstrap distribution. This is slightly different than the one we saw live there. But now we want to see how do I turn this into a confidence interval. And there's 2 ways we're going to do that. So the first way to get that is what I call the standard error method. And the basic idea there is we want to find the standard deviation of all those bootstrap statistics. So that several thousand bootstrap statistics we made, we'll find their standard deviation. And I tend to use the word standard error to talk about standard deviations, particularly for sample statistics. So standard deviation of X bars, I'll use the word standard error. Okay, so we'll use that bootstrap distribution to estimate the standard error. And then if we know that typically if things are nice and bell-shaped, we know standard deviation, things tend to be within 2 standard deviations of the center. So I take my original statistic and add and subtract 2 standard errors. That should give me a reasonable range of values where I can expect the population mean to be. Okay, so in our big picture here, we look up here for the standard error. Okay, and then we just take the original statistic, the 15.98 from my original sample, plus or minus 2 times that standard error, we get an interval from 11.71 to 20.25. And so that's my confidence interval. Okay, just simply statistic plus or minus 2 standard errors as a beginning one. Okay. Now, the second way we'll find the interval is to use what I call the percentile method. Okay, if you look back here, the reason this tends to work is we know that when I go 2 standard deviations either side, I'm capturing about the middle 95%. So I want to get rid of the things that happen 2.5% on the extremes. So I want to capture the middle 95%. And so given that, why don't we just do that directly? Just take that bootstrap distribution and find the middle 95%. So find the endpoints that cut things off. So we take 2.5% off of each tail, leaving 95% in the middle. So if I attempt to do the share more smoothly this time, Okay, we're back to our original distribution we saw here. And so if we go to the two-tailed option here in StatKey, by default, it'll assume a 95% confidence interval. So here's the middle 95% of our data. Here's the endpoints, and so 11.94 to 20.56. There's my 95% confidence interval. And the nice thing here is if I decided I want to do something different, like say I wanted to do a 99% interval, just click on that thing that's in blue, those are always editable, change that to 99%, and so now I've got roughly about 10 points taken off of each side, and now I've got a 99% interval. Okay, so by changing this number inside, I can change how much I'm keeping. Here's 90% keeping in the middle. Okay, take 5% of the dots off of each side. Now I've got an interval which gives me a 90% confidence interval. Okay, so try to come back more smoothly here. Come on, you can do it. Okay, so just a quick reminder here. So there's the 95% interval. Keep 95% middle, chop 2.5% off each tail. And of course, the usual interpretation for that. And then if we go to 99%, okay, chop 5% off of each tail, 0.5% off of each tail. And we get a wider interval that way. Okay, so looking at these two methods, I think it's good to do both of those because the first is really a good way for preparation for moving to traditional methods. Our usual statistic plus or minus some sort of a value times the standard error. Okay, we'll see how that comes up a little bit later. And the second way is really good for building and understanding what the confidence level means. Okay, so my students have really very little difficulty when I ask them questions like, which is going to be a wider, a 99% confidence interval or 95% confidence interval. That's just so obvious to them, they don't even have to think about it. They just know that you're going to have to take more percentages, it's going to have to be wider to get that. Okay, so that's one example. You got some idea of now what bootstrapping is. And the nice thing is the same thing works for lots of different parameters. So if I can do a confidence interval for a mean that way, I could do a confidence interval for any other statistics that I want to calculate for a sample. So proportions, differences in means, correlations, slopes, standard deviations, all work the same way. Okay, but let me pause briefly there just to see if there are any questions that have come up so far. And so, Julie, I'm not sure if you're managing the the questions or anything that's come up so far that I should take a minute to talk about.
Yes, just a second ago, one came in about the two methods. The question was, do you have a preference on the two methods, and if so, why?
Certainly, I think both are important. If I was choosing only one, I would go to the percentiles because that gives you the flexibility of doing other levels. And it's harder. You're stuck with 95% level when you're doing the two standard errors. So I would, if I was only going one, I would do the percentile. But where a lot of people really use bootstraps in practice is to estimate that standard error. And that's generating the two standard error confidence interval. So I would certainly strongly recommend doing both. If you had to do one, I would go with just the percentile.
Okay, that was the only question so far. You guys can keep them rolling in, and at the end, we'll take some more then.
Okay.
Okay.
All right, so we will go on to a second example just to see how other proportions work as easily. So what proportion of statistics students use a Mac? You might think about, I'm not sure at your school what that would be, but you might think, what that proportion might be for your students. We're just at a campus where almost all of our public computers are PCs. Okay, but a lot of students seem to have Macs. And so one of the things we do in our intro stat course is we do a survey. One of the questions we have is, what sort of computer to use? And so in the last survey this semester, 172 stat students, 118 have a Mac, or are Mac users. Okay, so we get a proportion there. It looks like about 0.686. And so same question, right? How accurate is that sample proportion? That's based on just this sample of 172 students in this one semester. How likely is that likely to generalize to a broader population? Okay, so we want to find a 95% confidence interval for the proportion of statistics students that use a Mac, and we'll just go right to StatKey on this. So seems like I have to new share twice to get that to work. Okay, so we're back in StatKey, and again, you're only one level deep. So clicking back on the StatKey icon takes you back to the main menu, and now we'll back down here for a confidence interval for proportion. Okay, now there are some built-in data sets. This isn't one of them though, but especially proportion data is very easy to enter because all you really need to know is the counts. So I go to edit data, it's going to know the count, which was 118 Mac users with a sample size of, I think it was 172. Okay, and that confirms here our proportion of 0.686. So that's our original sample. if I generate one Bootstrap sample, what's actually happening is it's taking those 172 people, it's randomly picking 172 with replacement from them, so different ones will get different MAC users will get used multiple times or not. And in this particular sample with the replacement, we get 113 MAC users. So that's one Bootstrap sample. The proportion shows up down here. And of course, now you're ready to go to, okay, 1,000. Okay, that's nice. You can still see the dots, but we'll go to a couple thousand. Okay, and you kind of lose the dots now. But 5,000 is usually a pretty good number. Okay, and you see this nice distribution for what sample proportions should look like if we're sampling from a population with a proportion of about 0.686 successes. Okay, and then to get that to an interval, okay, we're going to go the same two-tail. Okay, and so we're looking at about 0.616 to 0.756. Okay, and there's our 95% confidence interval. I think that's what I asked for in this case. So let's go back to our slides. Okay, and in class I always make sure I get one on the slide just in case something happens to the technology. So here's this one here. Again, we can look down here to get the confidence interval, the usual interpretation for that. We can also go up here and look at the standard error. Okay, and so if we go statistic plus or minus 2 standard errors, we're going to, in this case, get the same interval. Now, you won't always get the same interval, and that's one thing you have to be used to when you're teaching with bootstrapping, is the old match the answer in the back of the book. Doesn't happen. Okay, you can still tell when their answers are reasonable. You can tell when students are off and they're not doing something right, but you're not going to be able to have all those people get exactly the same answer as you used to with traditional methods. And it's perfectly fine. Statistically, we don't mind to have a little variability in what the answer should be. We're used to that sort of thing. Okay, so there's a confidence interval for proportion. I think I'm going to do 2 more examples. So this one, we want to do a confidence interval for difference in means, looking at the average math SAT score, comparing male and female students. This again from some of our survey data. And the other question I want to ask for that same data is to find a 90% confidence interval for the standard deviation of the math SAT scores based on that same data. In this particular case, the data is not available automatically in StatKey. You can get it if you go to lock5stat.com. There's a section there on data files. This is one of the data sets in the book, but not one we built into StatKey. But I did want to show you a little bit about how StatKey you can bring in your own data. So let me go back over here to StatKey. I'm getting better at this. Okay, so come up here, we're going to a confidence interval for difference in means. Okay, so one option is you can always just go to edit data and erase whatever data was there and paste in your own data, which you may get out of a spreadsheet or not, something like that. But the new one, we just actually put this in for this semester, is you can upload a file as long as you have a CSV file or a TXT file. So here's a bunch of data sets, and somewhere down here should be the student survey. Okay, so as long as you've got a TXT file or a CSV file, and most stat packages let you export things in that. So here's the student survey data. I'll bring that into StatKey. Now in this particular case, I want one quantitative, one categorical variable. So I want the math SAT scores, which are sitting here. So I'll highlight that. And I want gender, which is back over here. I'll highlight that. I'm ready to go. Okay, so here's my 2 samples. And we can see that for the males, the average SAT score is about 618. For the females, just under 600. The difference in means is about 19. We've got 193 males and 169 females. So I know I got my data in there. Things are looking good for that. This is nice because it does allow students to easily bring in their own data when they're doing their projects. And I often have students do their own project data and then do the analysis in StatKey. So when I generate my one sample now, okay, now what it's doing is it's taking Bootstrap samples from each group separately. So out of the 193 males, it chooses 193 with replacement, finds that mean, in this case 6.139. Out of the 169 females, it takes a sample of 169 with replacement. That shows up down here. And so for this particular Bootstrap combination, I get a difference in means of 8.78. Okay, so that's what's important. What's being repeated is taking a sample within the males to get the males, within the females to get the females. Okay, and that's what I'm going to do several thousand times. It is pretty quick. Okay, this works even on phones relatively well. So here's several thousand samples. Okay, and then if I want, I think I want a 95% confidence interval for the difference in means. Notice this is centered roughly where the difference is in the sample, as it should be. Okay, go to two-tail. Okay, so it looks like my confidence interval is that I'm 95% sure that the average math SAT score for males is somewhere between about 5.1 and 32 point, almost 33 points higher than the average math SAT score for females. Okay, and I could also use the plus or minus 2 standard error. Put the presentation mode on so you can see that, the plus or minus 2 standard errors for that one. Okay, so there's a difference in means. Let's try one more, back to StatKey. Now I want to do the standard deviation. So I'll go back to this one. This is for a single, again, this is sort of organized in one variable, one quantitative, one categorical, and so forth. So one quantitative would be standard deviation. Okay. The nice thing is that once I've uploaded a file, it's still there. So I can decide which column I want to work on. And I'm going to still keep with the math SATs. So as long as you're within that browser session, that uploaded file is still there as you go from different procedures within StatKey. Okay. In fact, it'll even show up, if you look at it, it shows up in the menu here as one of the menu items when you go to that. Okay, so now I've got, this is just the math SAT scores themselves, not broken down by gender. And let's see, the standard deviation looks like 68.5, pretty close. So all I have to do is make sure that what I capture in each bootstrap sample is not the mean. I want to capture the standard deviation. Okay, so now when I do one bootstrap sample, usual process down here to take a sample with the replacement, the standard deviation, this one was 67.2726, that shows up here. Again, you get the idea now. Do this several thousand times. Okay, we want a particularly 90% confidence interval, so I do need to use the percentile method. Okay, now here's 95%, change this to 0.9. There's a 90% confidence interval. So I'm 90% sure that the standard deviation in math SAT scores is somewhere between about 64 and 72.7. Okay, and that's one of the things I really like about the simulation approach is I can have my students after just one class and give them a homework assignment and ask them to find a confidence interval or standard deviation. Whereas in the traditional course, I would never even have them do that because I don't have a good formula for that. So back to the PowerPoint. Okay. All right, so that was just a reminder to make sure I went to StatKey there. That's good. So a little bit about making the transition to traditional methods, because again, we do want to make sure that when students are done with the course, they still know what a t-interval is, and they can still do traditional methods. So if we look at, here's the four examples we've done fairly quickly today, and what you notice for each of these, that we see the same sort of shape. And so by the time my students have seen lots of bootstrap distributions and also some randomization distributions for tests, they've seen the shape over and over and over again, the same bell shape. Okay, so they're really ready now to say, you know, we've got a theoretical model for that. That's a normal distribution. And so they're primed and ready to look at a normal distribution. And now we say, okay, how are we going to apply this to a confidence interval? Okay, well, let's go back and think about our statistic plus or minus 2 standard errors and say, well, where does that 2 come from? Okay, that 2 really comes from looking at this normal distribution and find the middle 95%. Okay, so actually it should be 1.96. We run it to 2 for convenience, but that's where the 2 comes from. So now you see, if I've got this normal distribution, and now I say, well, I want to find, say, a 90% confidence interval, all I should have to do is change what this number is, get a different endpoint, and I can get the distribution there. So switching back over quickly to StatKey. Okay, we'll come back here. So now we're going to use the theoretical normal distribution. There's the standard normal. And one thing that's nice for students, it's the same operation. You go to 2-tail. You find 95% of the middle, you cut 2.5% off of each tail. And you want to change that to 90%, just change that number in the middle to 90%, exactly as they did with the bootstrap distribution. They do that now for the theoretical normal distribution. So now I should multiply by 1.645 instead of 2. And that's really all they need for this part of the transition. Come back over here. Okay. So basically now it becomes statistic plus or minus z star, where the z value is chosen just like this to give whatever level of confidence you want. So this part is a pretty easy transition. We're just replacing the 2 by something we're getting off of this normal distribution. Okay. The other part of the transition is to replace this standard error, which now we have to do by simulating several thousand bootstrap samples. Okay. Now we say, well, if we can find a formula for that standard error, okay, and if we have conditions that tell us when we have a particular known distribution that we can use, say, that z star, then we should be able to find the confidence interval directly. So for example, we're looking at a confidence interval for proportion. Okay, We know we're going to use the p-hat for our sample statistic. Okay? The new thing is, here's a magic formula which tells us the standard error, square root of p times 1 minus p over n. Okay, so now we have calculated that standard error. This shortcut's having to do the thousands of simulations. Okay? And we've got some conditions about what the sample size has to look like in order for the normal distribution to be reasonable. Okay? And one of the nice things about doing the bootstrap approach is we can actually check these conditions and see why they're reasonable, and also confirm that this formula is doing what we want it to do. Okay, so here's what now you're nice and familiar, our formula for the confidence interval would show up that way. Okay, but we can look here and verify that if, for example, we take a situation where n times p is, n times 1 minus p in this case is a lot less than 10, we only have three no's and 27 yeses, we can see when we look at the bootstrap distribution that we don't see a normal distribution. Okay, that things bump up against the boundary at 1 here, and so we're losing one tail in the distribution. So it's quite clear why this should not be a normal distribution. Okay? In the same way, if we bump our sample size up, we can still keep the 0.9. If we take a sample size which is big enough to satisfy our condition of at least 10 yeses and 10 nos, okay, then we do get the normal distribution. And as a bonus, we can also confirm that this way of calculating the standard error shows up and will match pretty well the standard deviation, the standard error we see in the bootstrap distribution. So all this becomes then is a game to say, what's a good standard error formula, and what's conditions do we need to make the normal distribution or the t-distribution, whichever one, work out there. And that makes it pretty quick to go through lots of the traditional methods. Okay, so actually one of the comments I'm going to make on that, it's also important because you're probably thinking, if I spend some time doing bootstraps and randomization methods at the beginning, then I'm not going to have enough time to do all the stuff I usually do. And what we really find out in doing this is that you can go through the traditional methods very, very quickly if all you have to do is saying, what's the right standard error and what are the conditions you need? The important thing to know there is they already understand what a confidence interval is. So you're not trying to teach what a confidence interval is at this time. You're just trying to say, here's some tricks that will help us calculate it more efficiently. But all of the framework for understanding what a confidence interval is, understanding what a p-value is, that's already been done with the simulations. So you can go through the traditional measures much more quickly if all you have to do is figure out what the standard error should be. Okay, so a brief look at why the bootstrap works, because I know a lot of people, especially math folks I talk to, say it doesn't seem right that you should be able to use the sample to say how variable the sample statistic is. Okay, so this is something I come up with for showing my students. And I often have this big green blob, which I call the population. And then we have the balancing point, which is the mean. Okay, and so we're going to turn this into a tree. So there's the tree, the trunk of the tree is the mean holding up the population. And if we think about what we usually do for a sampling distribution is we take a sample of that population, that's the seed dropping out of that tree, which falls somewhere around the trunk, which is the mean. Okay, if we take a different sample, it may be below the mean. Okay, each sample we take, some may be close, some may be farther away, but the way we build a sampling distribution is to think about taking lots and lots and lots of samples out of that population and keeping track of their means. Okay, so that gives us a sampling distribution. And that's kind of the traditional idea of what a sampling distribution is, even though it's never really practical to take lots and lots of samples from the one population. So our problem is we don't get to see the tree. We don't get to see all these samples. We get to see just one sample. Okay, so the tree's gone. The tree's been cut down. All the seeds have been swept up. There's just one seed left. All we get to see is that one X bar. So now what can we do if we just have that one seed? Okay, and obviously if we had lots of time, the idea would be we'll grow a new tree. And that's exactly what the bootstrap procedure does. It takes the information in that sample, all the genetic information about that tree, and it grows a new one. Okay, and that becomes our bootstrap population. Now, it may not be centered at the right place because we know this is going to be centered at X bar. Okay, not necessarily the population mean, but as we drop samples from that bootstrap population, what we're assuming is the variability we're seeing in those samples is similar to the variability we would have seen from the original tree. Okay, so we grow a new tree of the same species. We say, well, how far did seeds tend to fall from the base of this tree? Okay, and so we want to estimate the variability in the X bars by looking at the bootstraps. Okay, and then assume that's going to be somewhere that whatever's a reasonable range of those, the mean is also going to be captured in that range. Okay, so I think it was Chris Weil had a good way of describing this. Said we use the bootstrap errors that we can see to estimate the sampling errors that we can't see because we can't generate lots and lots and lots of samples. Okay. And so this gets us to what I often call the golden rule of bootstraps, which says the bootstrap statistics are related to the original statistic, as the original statistic is related to the population parameter. And you can see that in the tree example here, and that the bootstrap statistics, that's all these ones that we've drawn here, are related to the trunk of their tree. Okay, the typical distance away is the way that particular sample, so that's the X bar, is related to the trunk of the tree it came from. So we find out what's a typical distance for seeds to fall away from the trunk, then we can say, well, this tree, this particular seed is probably not more than that from the trunk of the tree it came from. And so that's kind of why the bootstraps sort of work as we go along there. Okay, so just several final thoughts here. I hope I've convinced you that Bootstrap is a way to introduce students to the management of confidence intervals. Okay? And the nice thing is it requires very minimal background. That stuff that you've got early in the course, how do you take a sample? How do you calculate a mean and standard deviation? That's really all you need to be able to use the Bootstrap methods. It's also nice that they're easily generalized to lots of parameter situations. The traditional methods, every time you go to a new situation, you've got to learn a new standard error formula. Okay, whereas for the Bootstrap method, once you've got the basic method down, it applies very nicely to lots and lots of different ideas. Okay. Finally, we found that the Bootstrap distribution really appeals to visual learners. Okay, the idea of seeing the dots falling in that distribution helps them when they start to then transfer to the normal distribution. They have that picture, and so instead of counting dots in the graph, we're finding area under the normal curve. Otherwise, it's the same basic idea. So it really appeals to people who have that sort of visual, not necessarily formulaic approach to things. Okay, you do need some sort of technology. Again, StatKey will work for this. It's freely available. Jump, there's some other stat package that will support Bootstrap type calculations. I think in Jump, actually, any statistic you calculate, you can right click on and it'll generate a Bootstrap distribution for you. Okay, the thing that's nice is it leads smoothly to traditional methods. Okay, and it is important that we do think students still need to see the transitional methods. Okay, you can still get those done relatively efficiently and can all still work in a regular course. So I think that's about all I get for now. So I thank you for listening. And I actually think I almost finished on time, leaving time for questions. There's my email address and the address for where the materials are for lock5stat.com. But I think we'll take some time now. Julie, got any questions for me?
I sure do. I've got 3 of them.
Okay.
So the first one came up right after the break from the questions the last time. And it was, does it matter what the initial sample size, N, is that you're bootstrapping from? Does it matter what size you start with?
That's a good question. The one thing that's important is you should always, your bootstrap sample should always match the size of your original sample. Okay? As with most statistical procedures, you're going to get better results with a bigger sample. Okay, and so when you take a really small sample, okay, you'll see the bootstrap distribution is going to tend to not look so normal anymore because it only has a few different values you can get. So for very small samples, you only have a limited number of possible values when you look at the bootstrap means, and so the distribution may not look very good when you do that. Okay, and so there's not hard and fast rules like n bigger than 30 or that sort of thing, but as always, the bigger the sample size is, the more reliable your results are going to be.
Okay. All right, we've got another one that said, could you differentiate between the 3 randomization methods when computing a confidence interval for the difference of means?
The 3 randomization methods. I don't know what the 3 randomization methods are. I may need to get some more clarification on that.
Okay.
I do know, I can take a stab at that.
Okay.
I think what you're looking at there is when you're talking about doing a randomization test for a difference in means, then there's several different ways you can generate simulated samples to make sure the means are the same, the means are the same in the matching the null hypothesis. So you could do things like put all of that in one big sample and then take 2 samples out of that, okay? Or you could just scramble one of the samples and reassign the labels. There's several different ways of doing that. The thing that's important is that's for dealing with a randomization distribution for a test. And that does tend to have more different ways you can possibly do the randomization. One of the beauties of Bootstrap is there's only one way. Take a sample with their place from the original sample, nothing else you have to mess with. You don't have to do anything to make a null hypothesis true. So it's a much simpler procedure in some ways than possibly doing randomization procedures, which can get it a little more complicated as the difference in means example would illustrate. So I'm guessing that's what that question was dealing with.
Okay. It was about 3:41 p.m., so I don't know what you said that triggered it, but
I would do the difference in mean example, and someone has done a test for difference in means, which then does have the variety of different ways you can do that.
All right, then just a few minutes ago, right here at the end, the last question that I have in the box is, probability is the foundations of statistical inference. Do you teach simulation methods for estimating probability?
Sure. And again, I don't teach a lot of probability in my intro stat course. I teach a probability course, and we'll use the simulation methods a lot in there also as a way of kind of confirming things you might want to see from intuition, or in cases where it may be intractable to do the exact distribution. So certainly for that, it's another great way of using simulation methods.
Okay. Oh, they're flooding in now, Robin.
Okay.
So here we go. So I sense / you suggested that you feel that taking the time to introduce bootstrapping is recovered by the ease of teaching traditional methods later. That's a question mark. And then
Yes.
also zero sum on total time with better understanding, question mark.
That's exactly, absolutely on both of those. Someone was paying attention and got the point. Whether they believe the point or not is a different issue, but at least someone got what I think is the main point there.
Okay, awesome.
I do want to comment on one other thing, which I forgot to mention, and it may come up in the questions, is to what extent do students have to have technology to do this stuff? And so I should mention that I teach in a computer classroom, which is a very nice situation. So I can use it anytime I want in class. But I know lots of people use this in other situations. My wife intentionally teaches in a non-computer classroom. She just has one projection screen. Her students work just fine doing this also. My daughter Carrie, when she teaches at Penn State, she's in a lecture with 200 biostat students. Okay. And they have a once a week lab where they get some things. So it's certainly not the case that students have to be on there using stuff. StatKey is simple enough to use. If they watch an instructor use it, they can usually figure it out pretty well on their own. And a lot of it is just really good for doing demonstrations in class anyway. So I know that question probably is going to pop in terms of technology. I think I'll short circuit that.
Great. We've got one more here in the chat box, and it is, how do you emphasize to your students that the inference from the Bootstrap distribution, and in parentheses, and the permutation / randomization distribution rely entirely on the assumption that your original sample size is representative of the population?
Yeah, and that's just something you always have to emphasize. And I make that point that it does seem kind of magical, but if you've taken a biased sample, you're stuck. It doesn't automatically say, oh, you've got a biased sample, I know exactly how to correct that bias, but it won't do that sort of thing. So the usual assumptions of you've got to have a good sample technique, those are still present. And if you do have a bias in the way your sample is collected, you're going to get still erroneous results, and you're not going to capture the mean as often as you want to capture it. And that's still there.
Okay. Is there anything else from the participants? I haven't seen anything else come through either the question and answer box or the chat. I did share the link to StatKey in the chat window. Also, Robin has agreed to share these PowerPoint slides with us, so we'll have that as well, so you can get like the links and the ideas that he talked about. So this is really not a question, but it's a great job, Robin, which I have to agree with. If you guys could all thank him in the chat window, that would be great. This was excellent. Thank you very much. Are you ready for me to turn it over back to me, or?
Yep.
Okay.
Can I get back to you? And
super.
So I need to do, just stop sharing, right?
You could. I could boot you, though.
Oh, you could have done that a long time ago.
I could. Let's see. I'm going to go ahead and get back to mine. And I'm not as slick as you. See, mine wasn't showing. You did excellent at those transitions, by the way.
I got that one where it came back and gave me the screen I was just looking at. I kept saying, why didn't it change? I don't know why it didn't change.
Yeah, totally awesome. I wanted to thank you all for participating in today's webinar. If you'd like to support future AMATIC webinars, please consider becoming a member, bit.ly/join-amatic. Okay. We are on social media, so check us out on Facebook. We do also have a Twitter account as well. This is the bit.ly that you can get the recordings that Robin mentioned earlier in the webinar, bit.ly/amatic-webinars. And this is also in my signature, so any email from me, it's got this here as well. So it takes about 1 to 2 weeks to produce and upload the recording, which we will do as soon as possible. If you need to have a certificate for attendance today, you have to fill this out. I need you to fill out the evaluation. You can do this bit.ly, or let me go ahead and grab the URL for the survey directly from SurveyMonkey. And I'm going to go ahead and put that in the chat window on my other identity here. Let's see. There we go. So that should have showed up there in the chat window. Please take a minute to do that. Let us know how things went. And if you do need to request that webinar certificate, that's the way to get it, is to fill out the survey. I'm going to go ahead and stop recording.